Assalamualaikum and hello everyone. In this video, we are going to focus on spanning set. So before this, you have learned linear combination in vector space. So now we will continue with spanning set. So what is spanning set? Okay, let S be any vector. Let's say V1, V2 up until Vn. Okay, so this set S be a non-empty subset of vector space V. So set S is a subset of vector space V. The set S, this set S here, spans vector space V if any vector in V is a linear combination of S. So that means any vector in V, we can write it in this form as a linear combination of vectors in S. So B, any vector, equals to C1, V1 plus C2, V2 plus up until Cn multiplied with Vn. And provided that the C values here can be any constant. Okay, in other words, let's say I have V1, V2 up until Vn. So these are the vectors in vector space V. The set of all linear combinations of V1 up until Vn, the set of all linear combinations of vectors in vector space is a subspace of V. Okay, so that is called the space spanned by this set S. Okay, and it is written as this one, spanning set S is equals to the spanning set of V1, V2 up until Vn. So this means the span of S, the spanning set, is actually the set of linear combinations of vectors in vector space V. So the C1, C2 and up until Cn are also can be any constant, can be any real number. So based on the first definition here, so this V can be any vector in the vector space. So we can write that vector in linear combination of the vectors in set S. Okay, so this vector here, any vector V, can be vector in the form of polynomial and also can be vectors in the form of matrix. So if my vector space is real number space, so my vector, my any vector V should be in the form of, okay, so it should be in the form of any number x1, x2 up until xn. Okay, but if my vector space is polynomial of n degree, so my any vector V should be in the form of a0 plus a1x plus a2x squared plus up until an x power of n. And let's say if my vector space is matrix of m by n size, so my any vector should be in this form, in matrix form. A11, A12 up until A1n, and the last element here should be the last element A of mn. Okay. Okay, now let's try one example. Example number 3. This is example number 3 in your lecture notes. Consider set M, P, vector P, Q, and vector R, where P is x squared plus 2x minus 1, Q is 2x squared minus x, while R is 5x plus 2. Okay, determine whether set M spans P2. So this is our vector space. Our vector space is the polynomial with degree 2. So if your polynomial of degree 2, your vector space should be in the form of A0 plus A1x plus A2x squared Okay, so only up until degree 2 here because polynomial of degree 2. Okay, so the given vector m here, p is p value x squared plus 2x minus 1, q is 2x squared minus x, r is 5x plus 2. Okay, so from this polynomial form of vectors p, q, and r, maybe I can write this in the form of something like this. 1, 2, negative 1. 1, 2, negative 1 here refers to the coefficient of x squared, x, and also coefficient of constant, x power of 0, the constant term. Okay. For the next vector, the vector q here, so 2 and then negative 1. The last one is 0 because we don't have the constant term. Right? Okay. And the last vector, vector r, 0 because coefficient of x squared is 0. And then 5, 2. 5 is the coefficient of x, 2 is the constant term. So these are the vectors in M. Okay. Now our vector space is P2, polynomial of degree 2. So refer to this polynomial form of vector a0 plus a1x plus a2x squared. Okay. So that means the vector space, because I write M in coefficient form like this, so the V is just a2 because I start with x squared here, so a2, a1, and then a0. So this is the any vector in the space P2, in vector space P2 here. Okay. So now to test whether set M spans P2, you must be able to write set V, this set here, as a linear combination of all sets in M. Okay, so how to do that? Okay, we know that linear combination, if we can write something like this, vector y equals to c1 v1 plus c2 v2 plus up until cn vn. Okay, so for this one, okay, so this is my any vector a2 a1 a0, so a2 a1 a0. So this is my first vector v1, the vector p. So c1, any constant, multiply with the vector 1, 2, negative 1, plus c2, multiply with the second vector 2, negative 1, 0, plus c3, the third constant, multiply with 0, 5, 2. Okay, right. Okay, now to know whether we can write this as a linear combination, you must be able to find the value of C1, C2, and C3. Okay, so how to find the C1, C2, and C3? Okay, next step is to transform these into linear equations. So you will get something like this here. So this is system of linear equations. Okay, now you need to transform this system into matrix form. So this is the matrix form of this system of linear equations, right? You must solve the system. That means you must find C1, C2, and C3. If you can get the value of C1, C2, and C3, so that means you can write this vector as a linear combinations of vector P, Q, and R. Okay. Now, because this coefficient matrix here, let's say this is matrix A, because this matrix A is a matrix of 3 by 3, the size is 3 by 3, so this is a square matrix. So for square matrix, to know that the solution is exist or not, to know that whether the system is consistent or not, you can test with the value of the determinant. Okay, now find the determinant of A. Okay, so determinant of A, the value is -20. So since the value of determinant of this square matrix does not equals to 0, that means this system is a consistent system. So if the system is consistent, that means we can have values for C1, C2, and C3. And if we can have values for C1, C2, and C3, that means we can write this vector as a linear combination of vectors P, Q, and R. Okay, so if we can write that as a linear combinations of P, Q, and R, therefore we can conclude that the vector P, Q, and R here, the set M here, span P2. Let's try another example. Determine whether the set P spans R3. So R3 is the three-dimensional vector space. Okay, so this is the first vector in set P, second vector, the third vector. So in this vector space R3, any vector is in the form of x1, x2, and x3. Okay. So now we must write down this vector as a linear combination of these three vectors in set P. So you will get something like this. So from this, you can write into system of linear equations. Okay, and from that linear equations, you can transform it into matrix form. So in matrix form, you will get something like this. Okay, so from this matrix form, this is the coefficient matrix. Let's say this is matrix A. Okay, now you must solve this system. You must find the solution of this system. So you must find out what is the C1, C2, and C3 values. Okay, because the coefficient matrix is a 3 by 3 matrix, to state the behavior of the system, you can check by finding the determinant of this matrix A. Okay, so determinant of matrix A is, okay, write down your solution here, write down your working here. So determinant of matrix A is -1. Okay, so since the determinant is -1 and the determinant value does not equals to 0, that means this system is consistent. That means there exists unique solution for C1, C2, and C3. Okay, therefore, we can write this vector as a linear combination of vectors in set P. Hence, the conclusion is set P spans vector space R3. Okay, next example. This example here. Determine if W spans R3. So for this one, please try this question and please share your answer in the comment section down below.